This bridge should not exist. This is the Mackinac Bridge, the longest suspension bridge in the Western Hemisphere. Its towers rise higher than a 55-story building. Its cables contain enough wire to wrap around the Earth 1.5 times. And it was built without a single computer. For decades, every engineer who studied this site walked away. The geology was wrong, the winds were lethal, the depth was too great. When it finally opened in November 1957, deliberately timed to arrive before Michigan's deer hunting season, it connected two halves of a state that had been separated since before the Civil War. It has stood for 68 years, survived everything the Great Lakes could throw at it, but today, in 2026, the Mackinac Bridge has a problem. And for the first time in its history, nobody knows how to fix it. The Straits of Mackinac sit where Lake Michigan meets Lake Huron, a 5-mile gap of open water between Michigan's two peninsulas. For over 70 years, building a bridge here was one of the most fought-over engineering questions in American history. The Upper Peninsula is geographically enormous, larger than Connecticut, Rhode Island, Delaware, and New Jersey combined. But for most of its modern history, it was economically stranded. The Michigan State Highway Department's answer, starting in 1923, was ferries. They called it the floating highway. Ferry traffic worked in batches: load, cross, unload, return. By the mid-1950s, post-war automobile demand had overwhelmed the system. The fleet could move roughly 9,000 vehicles a day, but that was never enough during peak travel. The real test came every November during deer hunting season. Traffic backup stretched 16 miles south of Mackinac City. Wait times reached 19 hours. And when the weather turned, the ferries stopped entirely. Wind packed ice into the docks and trapped boats in their own slips. The connection between the two peninsulas existed only with the permission of the wind. The floating highway was the only thing connecting two halves of a state, and it broke every winter. Bridge proposals had been floating around since the 1880s, more than 70 years of debate with nothing to show for it. The reason was always the same: it was the ground itself. Under the straits lies a massive glacial gorge running through the center of the channel at depths approaching 200 feet. The bedrock is a chaotic formation of broken limestone, crushed and re-cemented over millennia after ancient salt beds dissolved underground and caused the rock layers above to collapse. Geologists looked at it and called it a gravel pile. The straits also form a natural wind tunnel. In 1940, the Tacoma Narrows Bridge in Washington had been shaken to pieces by a 42-mile-per-hour wind and dropped into Puget Sound. That disaster killed the confidence of every bridge engineer in America, and the memory of it was still raw a decade later. And at nearly 200 feet in places, the channel was deeper than any bridge foundation ever attempted at that scale in open water. 3 separate problems, any one of them would stop a normal bridge. All 3 together made the straits a dead zone for engineers. David B. Steinman grew up in Lower Manhattan, in the shadow of the Brooklyn Bridge. He told the kids in his neighborhood he would build bridges like that one day. He meant every word of it. By the time he reached the Mackinac project, he had designed bridges on 5 continents. But 2 of his earlier bridges, the Deer Isle in Maine and the Thousand Islands in New York, had experienced serious wind-induced motion after construction. Emergency cable stays were added after the fact to stabilize both structures. He had warned the engineers building the Tacoma Narrows Bridge that the design was aerodynamically unsound. He published his concerns formally. He was ignored. Then the bridge fell. When Steinman arrived at the Mackinac in January 1953 as the appointed design engineer, he was building against his own mistakes as much as anyone else's. The rest of the engineering world wanted a graceful ballerina of a bridge. Steinman decided he would build a tank. The foundation work required the largest peacetime maritime fleet ever assembled in American history. Steinman's team built massive caissons, double-wall steel cylinders 116 feet across, wider than a 10-lane freeway. These were welded on land, floated into position and driven deep into the bedrock. After that, they were filled with coarse rock and grouted from the bottom up using a technique called prep-packed, where high-pressure cement was pumped upward like a piston, pushing water out and solidifying chemically. Man-made rock fused to the glacial floor. The gravel pile became a foundation. For the wind, Steinman made a decision that defined the entire bridge. The two inner lanes of the Mackinac are open steel grating, a lattice you can see straight through to the water 200 feet below. Drivers still find it unnerving today. The Mackinac Bridge Authority offers a driver assistance service for anyone uncomfortable making the crossing. But to the wind, those lanes are invisible. Lift forces have nothing solid to act on. The deck was designed to move up to 35 feet sideways in high winds. The towers themselves flex several feet. Every one of these movements is designed physics, built into the structure on purpose. He turned the roadway from a sheet of plywood into a screen door. Then there is the detail that separates the Mackinac from every modern engineering project. Every stress calculation, every load distribution, every structural model was done by hand. There were 12,580 individual wires in each main cable. Each cable measured 24.5 inches in diameter, about the width of a manhole cover. More than 42,000 miles of wire total. The engineers working on this bridge had no simulation software, no finite element analysis, and no computational models of any kind. They had slide rules, drafting tables, and mathematical reference books. Every number that holds this bridge together was calculated by a human brain, written by a human hand, checked by human eyes. One of the most complex suspension structures ever built exists entirely because of what the human mind could hold. Steinman was obsessed with safety. His stated goal was the safest construction project in history. 5 men died. 1 died in a driving accident, 1 fell in a caisson while welding, 1 fell into the water and drowned, 2 fell from a temporary catwalk near the top of the North Tower. Every wire in those cables was placed by human hands. Some of those hands belonged to men who didn't come home. On November 1st, 1957, the bridge opened. As the first cars rolled across, the state ferries gathered on the water below and blew their horns in unison. One final salute before their era ended. It was the sound of a torch being passed. The storms of the Great Lakes, the violent November gales that Gordon Lightfoot sang about, have never threatened the Mackinac structurally.
In the wreck of the Edmund Fitzgerald.
On November 10, 1975, those same storms sent the Edmund Fitzgerald to the bottom of Lake Superior. The Mackinac Bridge closed that night due to weather. Steinman's tank was still standing. The bridge remains over-engineered for its current traffic loads, still stronger than it needs to be. It's been directed by the state to operate as a self-supporting facility, funded by its own tolls. More than 11,000 vehicles cross it every day. It was designated a National Historic Civil Engineering Landmark. Steinman's tank won. But winning against wind and geology and depth, against everything this site could throw at a bridge, left one problem untouched. One that Steinman never designed for, because in 1953, nobody thought to ask about it. Every winter, freezing rain coats the bridge's cables and towers in ice. When temperatures shift, brief warm-ups followed by refreezing, the ice dislodges. It falls from the towers, more than 300 feet above the roadway, at terminal velocity. The pieces that land on the road deck have been described by bridge officials as garage door-sized sheets. Some form into ice spears up to 20 feet long. They have shattered windshields, they've damaged vehicles. Several times, conditions have been severe enough to close the bridge entirely. And here is the cruel irony. The open steel grating that made the Mackinac invincible against wind leaves the road deck completely exposed to what falls from above. Steinman solved winds by opening up the deck. The ice doesn't care. In the entire recorded history of ice closures at the Mackinac Bridge going back to 1995, the bridge had closed for falling ice 32 times, roughly once per year on average. In the winter of 2025 to 2026 alone, the bridge closed for falling ice 12 times. One season! That broke the previous record of 10, and it accounted for more than a quarter of all recorded ice closures in the bridge's tracked history. Communities on both sides of the straits felt it, from workers commuting to jobs to families trying to get kids to school. One closure that winter came close to triggering a fuel shortage in the eastern Upper Peninsula after supply trucks couldn't get through for hours. The bridge that eliminated the 19-hour deer hunting backup was now closing without warning, repeatedly, unpredictably. The bridge that never fails was failing to stay open. The Mackinac Bridge Authority's own public frequently asked questions states it plainly. There is very little that can be done to prevent this type of closure. There are no anti-icing or de-icing technologies on the bridge. Authority staff generally just have to wait until the ice stops falling to reopen. Salt is out of the question. It corrodes steel. The solution that works on every road in Michigan would destroy the structure it's meant to protect. Prediction is equally impossible. Unlike wind, which forecasts can model hours in advance, ice falls when temperatures shift in ways that follow their own schedule. The weather at the tower tops is different from the weather at the road deck. The Bridge Authority has noted that the National Weather Service found no increased frequency of freezing rain advisories around the bridge. But there have been more brief winter warm-ups in recent years, which may be contributing to the ice forming and then suddenly releasing. Nobody fully understands why the 2025 to 2026 season was so much worse than any previous year. In April 2026, State Rep Parker Fairbairn proposed a $600,000 appropriation to fund a study by Michigan Technological University. Researchers would examine structural conditions, road surfaces, and weather patterns to determine what is causing the increased frequency of closures. Designed by the man who predicted the Tacoma Narrows collapse before anyone listened. Built without a single computer. And the problem it faces in 2026 is one that a $600,000 study will spend years trying to explain, not fix. The bridge remains structurally sound. It will likely outlast everyone alive today. Steinman built that guarantee into every calculation. He conquered the geology, tamed the wind, and solved construction itself with nothing but human calculation and a drafting table. The one thing beyond his reach was a weather pattern that was invisible in 1953 and remains poorly understood in 2026. The $600,000 study will take years. The closures will continue in the meantime. This bridge should not exist. It does. And for 68 years, that was the whole story. But now there's a new chapter, and for the first time, nobody knows how it ends. What do you think should be done about the Mackinac Bridge's ice problem? Is it something engineering can eventually solve? Or is this a force of nature that will always have the final word? Let us know in the comments. Subscribe for more Mega Build stories.